everyone, I'm Xin from the Department of Mathematics, Xiamen University. Today, let's talk about directional derivatives. So far, we have considered partial derivative, which is how a function changes along x or y directions, like what we can see in this figure. But what if the changes happen in a diagonal direction like here, which the orange arrow pointed to? This arrow represents the directional derivative, the rate of change of the function fxy in a specific direction, not necessarily aligned with the axis. You can imagine we are standing on a hill represented by this surface, and we want to know how steep the slope is if we walk in this exact direction. Imagine you are climbing a hill, you are not restricted to just going north or east, you might move diagonally or even in any random direction. This is why we need directional derivatives to understand how a function changes in any given direction. The direction of change might not align with the axis. It might be increasing, decreasing, or remaining constant. Therefore, we need a consistent way to find the rate of change of a function in a given direction, defining the direction change of a vector as a unit vector u in Rn. Firstly, let's introduce the definition of directional derivative. Let O be an open subset of Rn containing the point x0, and let f be a function defined on O. Given a unit vector u in R, we say that f has directional derivative in the direction of u at the point x0 if this limit exists. So, the u has a length of 1. If u is not a unit vector, we will not call it as directional derivatives. When m equals to 1, which is the dimension of codomain, it is customary to denote the directional derivative of f as a single variable function in the direction of u at the point x0 as the directional derivative, which is the f is unbold, it is not a vector. Moving on, we have a proposition related to the directional derivative. The proposition says that the directional derivative of a vector value function exists if and only if all components' directional derivatives exist. And we need to prove the derivative of the whole function is just a vector made up of each component's derivative. The proof is essentially using the idea of component-wise convergence theorem. So we break down fx into components like f1, f2, and so on. And the upper one is the vector value 1 having the definition mentioned above, while this is the component's directional derivative. Then we need to show the limit of components exists, then the limit of whole function exists. Secondly, we need to prove for the directional derivative of a vector value function dvf equals to dvf1, dvf2, and dvfm. We first let fx equals to f1x, f2x, until fmx. Then by definition, we can write the vector value function in this form. And then by some simplification, we can have limit of the f1 x0 plus hv minus f1 x0 h, and similarly for fm. So we recombine the components into a vector which is dvf1, dvf2, and dvfm. These results help us handle vector value function elegantly. Now here's the powerful result. Let O be an open subset of Rn that contains the point x0, and let f be a function defined on O. If f is differentiable at x0, then for any non-zero vector v, dvf(x0) exists, and we can write in the vector form. It means that if the function is differentiable, the directional derivative in direction v can be computed as a dot product between the gradient and the direction vector. So let's prove it. So we just consider the case for f1, the others will be similarly. By definition, we have the limit of dvf1 if it exists, which is written as here. And recall that by a theorem we have learned before, which is this theorem, If f is differentiable at x naught, each of the components will be also differentiable. Like here, if f is differentiable at x naught, the component fj has partial derivative at x naught, and we can written as write something like this. So come back to here. Since f is differentiable at x naught, we can write the components f1 is differentiable at x naught and it has partial derivative at x0. We can write the limit equals to 0. By setting h equals to hv, we find that the limits of this equals to 0 and multiply both sides by the distance of vector, we get this equation, and then we move this part to the opposite side. We get the directional derivative of the first component is equals to the dot product between the gradient and the direction vector. So instead of computing limits manually, we can just calculate the gradient and take the dot product. Here's the beautiful conclusion. Let O be an open subset of Rn that contains the point x0. Let f be a function defined on O. If f is differentiable at x0 and the gradient is non-zero, then at the point x0, the function f increases fastest in the direction of the gradient. Visually, it's like standing on the slope and asking which way is steepest. The answer is go where the gradients point. It will be the steepest slope. To find f increases faster, we need to choose the direction of u so the direction derivative is maximum. By using the theorem above, we have the direction derivative is equals to the dot product of gradient and direction vector. So, by Cauchy-Squart's inequality, we show that the maximum directional derivative is achieved when the direction matches the gradient. If we choose u to be the unit vector, we will achieve the maximum as mentioned here by some simplification. That's why optimization problems often follow the gradient. It leads to the fastest increase. Let's go through an example. Here's a function defined as fxy equals to sin x squared plus y plus 5xy squared. We are asked to compute the directional derivative at 1 minus 1 in the direction of any vector v equals to v1, v2. We will first compute the gradient and then after that multiply by the direction vector. So the gradient is, we need to compute the partial derivative, which is fx and fy. So fx is equals to 2x cos x squared plus y plus 5y squared, and fy is cos x squared plus y plus 10y squared, 10xy. So we can substitute the fx and fy to the gradient, and we get this. Moving on, we can find the gradient, which at the point 1 minus 1, we get 7 and minus 9. We find that the directional derivative at the point 1 minus 1 is equals to 7 v1 minus 9 v2. That's all for the example. Here's the reference for this project, and thank you for listening. Bye bye.